Right, well, I think we can get started. Thanks for coming, everyone. This is day one of our graph section for the course. So today we'll go over a few topics. We'll go over disjoint set union, then we'll review minimum spanning tree, and we'll also look at Kruskal reconstruction trees, which are probably new for a few people here. So first we'll go into disjoint set union. So the crux of the problem is pretty much as so. So we have a graph and we have a few queries. And in these queries, we can either merge two nodes to get like two components together to say a group of nodes are like within like the same team or connected component. And then we can also find. And in find, we pretty much return like a representative for the connected component. So we can go over like a live demonstration just to, I guess, get a more intuitive understanding of how this works. So let's say everyone is like on their own team or just connected to themselves. And if I were to like run like a merge command for everyone, I would say, for example, everyone in the same row is part of the same connected component. So you can like, for example, look around and see who's in the same component as you. So you two would be in the same component as Eric, for example. And now I would query and say find, and I would say maybe for you two, are you in the same component as Eric? And I would have you guys like shuffle yourselves. And the difficult part of doing this would be naively, you would probably just remember he's all in the same row as you. And although this works for like small numbers, once you get into the tens of thousands that computers work with, it then becomes very problematic since every like 10,000 people need to remember the status of 10,000 other people, which can get very slow. So one way that we can think of actually solving this in a more memory efficient manner is just to remember one other person in your group in a structured way. So for example, instead of remembering everyone who's in your row, you could just remember like who's to your left. So for example, you would remember who's to your left, so it would be her, and then she would remember that Eric is to her left. And then if I were to shuffle you guys around, then you would know to just look to see who she's pointing at. And then eventually this chain would end where Eric isn't pointing at anyone, and then you would know that he's like the leader or representative for your component. So I guess we can just do a live, like just a demonstration. Everyone just like point to their left. Okay, so now let's see. You, for example, he would be like the representative for your row. The guy in the green jacket, right? So that's the way that would be a way to run an algorithm. And then to tell that he's in your group, you would just see that he also ends up pointing at the same person. It's a bit obvious here because he crossed him in your path, but in more complicated trees that wouldn't happen. But as you saw, there's like there's a possibility for long chains. For example, you had to go over him to figure out who your leader was. And you could think that if everyone was in the same row, the last person would have to go over like n different people, which can get very time consuming. Again, in the 10,000 example, one person might have to like look at 10,000 people to figure out like what component they're in, which is also extremely slow. And if you were to implement this in actual like computer code in Python, it will look somewhat like this. So to find out who your leader is for your component, you would just look at the person who like your parented or like pointing to. So parent X is who you're pointing to, and then you would see that they would also be pointing at someone, and then eventually you would get to a leader where we just say they're pointing at themselves. In which case, that's how you know that's what your component is. And then merging is also very easy with this. It's pretty much all of the root finding algorithm. You just find who leaders are for the two like people's teams you're merging. And then you just have one of their leaders point to the leader of the other person. Does that make sense to everyone? Okay, yeah. So in implementation, let's say we can merge 6 and 7. And in that case, the leader would be 7. And you could also merge 0 and 2, and the leader would be 0. And you could repeat this process, merging different components together. 3 join like the larger component there of 0 and 2. And then these two larger components also can get merged together. And this seems to work. But again, we have to run finds every time you join. And as we saw, that was very time consuming. So for example, here, when we wanted to merge like one, if you wanted to like merge like 1 into 0, for example, we kind of have to go through this like entire process of finding. We have to first go to 7, then go to 8, then go to 1, and then like we know that like the root is 0 in this particular example. And this gets pretty slow. So I'm gonna just ask, like, can we do better? Does anyone like have any ideas? Well, one way that like I look at this is that we already did a lot of work traversing this chain. So I think we can probably squeeze in some like of the length of the chain work to make our like lives easier in the future. So one way we can do this is through path compression. So we'll also do a live demonstration of this. Everyone again just point to their neighbor to their left. And the geometry is kind of hard, but now just look at who like the final person is in your row and then just point at them. Now like it's the same thing, but if you guys are more, it'd be a bit easier. But now instead of having to look at each person in your row, you could just look at the left. You could just look at the final person that you're pointing at. And you could just do this work when you define. Because when you define, you eventually define the leader. So there isn't a reason to like throw away all that work. And in actuality, you can do this for like every person that you like come across in the find. So it looks sort of like this, and it'll become more clear here. So again, if you were to run find and we go to nodes 7, 8, and 1, we actually we find out like what 0 is. And we already know like all the nodes that are like parented to 0 eventually. So then on our way back in our recursion here, where we have the parent of x is just equal to like what we found as the root, we can just compress the path by assigning them all back to be leader 0. And this sort of just terminates the long chains like over time. And this is like one improvement that we can make. But if you think about it, there's still a potential for long chains to occur if you're like inserting like one element at a time. So since like if you insert one element at a time, there's a chance you can like make like a very long chain if you don't run find too many times. So maybe is there anything else we can do on more of the merging side to improve performance, especially when you have like one like small tree and like one large tree that you're merging? The about like the size of the tree, yeah, the size of the tree matters. You can actually like merge by size, which is what we'll go into. So to avoid like the edge case where we create like long chains by like merging a large node into a large tree into a small tree, we can always merge a small tree into a larger one. And the code is pretty simple. It's only like 3 additional lines. And by doing it like this, you can do a complexity analysis where if you have like the current leader that you chose, which is the leader of the largest tree, when you merge the smaller tree into it, the other like the it's pretty much it's close to a binary tree. So the smaller tree has like another like sibling of the like leader. And pretty much you can see that every time you increase like the number of like leaders like depth, then like you have to like, pretty much get like double the size of that smaller tree. So intuitively, you can get a sort of like doubling of tree size as you increase the depth, which means that you have like a logarithmic depth with the size of the tree, which then means that since the depth is log n, then when you run the path compression in the find algorithm, you only have to like look at a logarithmic number of vertices, which improves our running time from O of n to O of log n. And it was only 3 additional lines for the union by size. So just like as a review, we need to be able to run union and find queries quickly. When we just use the naive approach where we had to remember everyone who's on our team, querying was very quick, especially if you use like a set data structure. You say, is this person in my like team set? But then you had O of n time for merging, since you have to augment your set by n elements every time you merge. And then it was n squared memory, because there's n people. You have to like remember at most like n different elements. When we did the parent pointers, where we had everyone like point towards each other, we saw improvements in some ways. The memory was much smaller. It was O of n memory. However, the query jumped from O of 1 to O of n, since we had to look at n pointers before actually figuring out what our leader was. And then via path compression, we're able to get down to logarithmic size, although we didn't do the analysis for it. And then the same for the union size, with the doubling of the tree size every time you increase the depth. That leads to logarithmic path size. But it actually turns out that if we combine these two ideas, we get this O of alpha n. And this alpha is actually called the inverse Ackermann function. And as you can see, I think the screen is frozen. So we're back. So like I was explaining, I think it's fine. Yeah, inverse Ackermann grows extremely slowly, with like just 2 to the 2 to the 2 to the 65,000. If you take the inverse Ackermann of that, it's only 4, which is significantly less than most things you would see. Logarithmic would still be like 2 to the 2 to the 65,000. So this is like, for all intents and purposes, like practically constant, but theoretically it technically isn't. I guess before we move on to minimum spanning trees, are there any questions about what we've been over? Yeah. Yeah, at the very end. We'll do a live coding of disjoint set union. So what we just went over. Yeah. All right. So yeah, we'll go over a minimum spanning tree next. So it's an application of disjoint set union where we want to just choose a subset of edges from a graph such that we minimize the total weight of the tree while managing to connect all the vertices still. So to do this, we run an algorithm called Kruskal. And the idea behind it is that you just take the smallest like remaining edge that you haven't added to your tree yet, and then you ask whether it connects to components of the graph that haven't been connected by a tree yet. So for example, if we were to use this example, 5 and 1 haven't been connected yet by the tree, where we represent the tree with the red vertices. So since 1 is the smallest, we choose that one first and we connect 1 and 5. And then we repeat this for the edge of weight 2 over here. Since 3 and 6 aren't connected by the tree, we just choose the edge of weight 2. We repeat this for the edges of weight 3 on the left and right side. And then we get these 2 components. And then we move on to edge 4, since that's the next smallest. However, we then ask, are 1 and 4 the same component? But as you can see, they're both connected by edges of weight 1 and 3, so they are. So in that case, we end up skipping 4. And then we ask the same question for 5, but again, vertices 2 and 3 are connected. So since 5 would be redundant here, we skip it. But then for 7, we actually include it because the left and right components were not connected before the addition of 7. Was that clear for everyone? All right. So for this particular graph, this S shape would be the MST. And the proof follows just from like a proof by contradiction. Inductively, you can assume that all the edges up to the edge you're adding are correct. And then you could just say the edge we chose to add like wasn't correct and we shouldn't have added it to the MST. That means there is some path where like one of the edges has where all the edges have like weight smaller than that edge we just added. But in that case, since we added the edges in sorted order, then that means that we would have added all those edges to our construction from earlier. But since we do a connectivity test, then that means that this blue path would have meant that we wouldn't have added this edge, since that means that A and B are connected here, which means that it's not possible for us to add an edge where like it isn't supposed to be in the MST, assuming the edges that we previously added were in the MST. And then using induction, that means that like all the edges we added were correct. Is everyone here like familiar with induction? Okay. Yep. All right. Okay, and then we can go into Kruskal reconstruction trees, and then we'll do the live coding. So it's very similar to the MST algorithm, but we'll just first go over like what the problem actually is. But you have like given just like a query of like two vertices. So for example, vertices like 2 and 3 here. You just have to return like the smallest number where like every path between like those two vertices, or at least there's like just some path between those two vertices where all the edge weights are like at most that number. And this also just happens to be like the max edge weight between like the 2 points in the MST. So for example, here 2 and 3, the max edge weight between them is 3. So you would just return 3 in this example. And you can just run the MST algorithm again, but just keep track of some of the information you're throwing away. You can just keep track of like which edges are included and like when. So for example, when we're running this again, when we connect 1 and 5 together, we just keep track that that edge was what we used for that particular connection. And then we create like a virtual vertex here representing the edge of weight 1, and we have nodes 1 and 5 parented towards it, and then we just treat that as a parent for that connected component. We then do that for 3 and 6 separately, and then for connecting 5 and 4 here, since 1 is like the leader here from like the disjoint set union, if you can think of it in that way, you would then choose that leader and then the leader for 4 being itself, and then we create another virtual node for the edge of weight 3 here. Does that make sense? You like these edges are also like vertices in the sum directed tree that we're creating. And then you can just repeat this process. And then at the end of this, you then just get a new tree here. And this is like the reconstruction tree. And it has a nice property where the result of our query is just the like lowest common ancestor of the 2 points. So for example, if you want to find like the largest edge separating 1 and 2, it's the lowest common ancestor in this tree, which is 7. And again, for vertices 2 and 3, the lowest common ancestor is 3. And for like, I guess a short intuitive proof for why this works, you can think of any path in the MST as being a path in the reconstruction tree. And then from that, you can see that every like ancestor here sort of corresponds to a path to an edge you're like traversing here. And that means that the highest like vertice in this path ends up being the highest edge weight since we added them in order. But we know that the lowest common ancestor has to be like the highest vertice. Otherwise, if you were to go to 7, for example, you would then have to go backwards, which would correspond to taking a path where maybe you go from like 2 to 4, then back to 2, which is like redundant. So the lowest common ancestor ends up being the highest edge in this path, which ends up being the highest weight edge within that path as well. So we can do a live coding for a DSU related problem. And this is route reparation. So we can just read through this really quick. But pretty much you have a graph and like a number of roads between like each city, and you want to be able to like choose the edges or roads in such a way where you minimize the total cost or like total edge weight. And if you look at the MST problem, this is pretty much just calculating the MST. And you'll see how the disjoint set union is helpful for this case. So you can just you can just code it up in the online ID. So you can do this from mostly scratch. So here we take in the inputs and just like parse the edges that we have here. And then we want to, of course, sort it because we want to add them like in order from like smallest cost to greatest cost. And then we want to implement the disjoint set union. So we have we want a find function where we just find like what the leader of our component is. And then we also want a merge function, which is like just union. I'll call it union, where we take like two vertices and then union their components together. So you can implement find first. Wait, actually, before we do that, were there any questions on the Kruskal reconstruction trees? Yeah. Yeah, they're given to you. Yeah. It technically depends on the problem, but like from the context of running this algorithm, you're supposed to feed this algorithm like the edge weights. Yeah. Right. Okay. So back to this. We can just use the recursive. Here, we're back. The recursive definition we had. So first, we check to see if the parent of the vertex is equal to itself. If this is the case, then it's like the leader of its component. So we just return itself. Otherwise, we know that the leader should just be what we find for the vertex we're pointing at. So we do something like this. And then we could return the leader. But to like speed this up, we want to implement path compression. So since we already like have the leader, we can just not throw away this information and just compress the path by doing that, which is what we did on one of the earlier slides. And now to find the union, we have to find the leader for both vertices. So let's say leader 1 and leader 2 are the leaders we found using the function we just created. And then we also want a union by size. So we'll assume that leader 1 is smaller, and just in case, just so we can assume that, we'll do if the size of leader 1 is greater than the size of leader 2, then we just swap them. And then here, so now we know that leader 1 should have a smaller size than leader 2. So we merge leader 1 into leader 2. And to do that, we just set the parent of leader 1 to leader 2. And then, of course, because we updated the size of the leader 2 tree, then we do size leader 2. We just add the size of the tree we just merged into it. Right. And now if we go back to the problem statement, we have to run MST, and then we have to return the total edge weight. So we can keep track of the total weight here. So the total edge weight, we can say it starts off at 0. And then we can just leap draw the edges. So for A, comma B, comma W in edges. Oh, and then also for this loop, it's helpful to know if the union succeeded. So we can also just check that really quick. So if they're already in the same component, then the union fails. So we can do if leader 1 equals leader 2, which means they're in the same component and we can't like union them anymore, then we just return false for a failure. Otherwise, we return true after doing the full merge. And now we can do merge equals, we got a union A and B together. And then if we fail to merge, actually let's just do this. If we succeeded in our merge, which we can just do that actually. Then that means we added the edge to our graph, or in this case, the road to the like repaired road list. We just add the weight of the edge. And then we also want to return like if it wasn't possible. So there's a case where just the original graph we're given was like disconnected, in which case like no MST will be able to fully connect the graph. So we also want to keep track of the number of connected components. And then if the number of connected components is 1, then that means the entire graph is connected. So we can also keep track of the number of connected components as well. And the useful property is that every time we like union, we remove like one component. So we could just like subtract the 1 from our tally. So now if the number of connected components is 1, then we know that we succeeded, and we can print out the total cost we incurred. Otherwise, we know we failed, and then we just print impossible. Does this make sense to everyone? We can also submit this to be judged to make sure it works. Then also in the example, we returned 14, which is correct as of here. So we can, so we'll just submit this and see if it works. And then if we don't, we'll have a live debugging session. So let's see. It takes about like 20-ish seconds. Right, yeah, and that works. So that's how you would solve this particular problem. It's just a mix of like DSU and MST. It's a pretty simple algorithm once you know it. I would say most of the difficulty is just being able to like read the problem and then being able to apply like what you already know to it. Were there any questions about the implementation or anything that was like unclear about this, or is it pretty clear to everyone? All right. Well, that wraps it up for most of the Graphs 1 lecture. I'd recommend filling out the feedback form, and I'd recommend coming to the advanced lecture since it seems like most people had the hang of this one.
Yeah, and also one more thing, our raffle, we'll hold our raffle tomorrow just to let everyone get in their raffle counts. Yeah.
All right. Yes, yeah, I recommend coming to the advanced lecture tomorrow. We'll go over some more difficult topics.